Welcome. For those of you who I haven't had a chance to meet, Kingsley Hall, Chief Executive of MicroX, Anthony Skeats to my left is going to make a presentation on our unique technology platform shortly and take you through some of the applications. Patrick O'Brien, our chair of our board, is also here. Pat, Ant and I will be around, as will all of the management team throughout the day. So if you've got any questions, please just come up to us at any stage and ask it. We'd love to explain anything to you. I think you'll really enjoy today. It's about the fourth or fifth investor day that we've held, and we'd like to do it every year. We've had a couple of things in the past few years that have prevented us and prevented people from travelling, but we're now back on track. So as I mentioned, Ant will make a presentation for about 25 minutes, half an hour. We'll then go back across to our office, a bunch of tours, probably in groups of 7 or 8, I'd imagine. The tours will take about an hour. They'll stop at 7 or 8 different stations across the facility, where you'll get to meet some of our really talented staff who are all subject matter experts in the stations that they'll be presenting. I think everyone that's been on the tours before loves it. It's engaging, gives you as shareholders a great opportunity to see what we're doing, the products we're developing, and kind of get some hands-on experience of our company. I will be brief. Anthony's our Chief Operating Officer, also our Chief Engineer, has been with the company and been involved with the technology and the product development longer than anyone else. Is best placed to give this presentation on the tech this morning. And then as we tour around, we'll be more than happy to answer any questions you might have. So that's enough from me. Over to you, Ant.
Thank you, Kingsley, and thanks everybody for coming to listen today. I'm not sure what background everybody has. I'll try and keep it simple, won't go into too much of the physics, but I wanted to spend a bit of time today explaining a bit more about what MicroX has delivered since its inception in 2011. And I'll start with the entry slide here, creating revolutionary imaging to better lives. That is our purpose. We re-established our purpose a couple of years ago when we looked at ourselves as a business and thought, what is it that we're really about? What really drives our staff? What drives our customers? And this kind of tagline really resonated with us, along with our values of being curious, collaborative, and determined. We were founded in 2011. I'm sure some of you know that already. We have the facility here in Tonsley. We also have a facility in Seattle, and we have an office, registered office in the UK, which is primarily focused on sales. All the R&D and production and development work is done here. And in the Seattle office, we have a centre of excellence around software imaging, because in the Seattle location, there's a lot of software engineers of very high quality and high skill. Also, our chief scientist, Brian Gonzalez, is located there. We were the first company in the world, and we remain really the only company in the world to have commercialized CNT technology, carbon nanotube emitters. I'll explain a bit more about that in a second. And our first product, the rover, we've now had over 400 units sold in 39 different countries. We have a lot of government contracts on the way at the moment for our future products in the CT space, and we're starting to get a lot more traction now with the clinical fraternity and our customer base. So let's start with what we call nano-electronic X-ray, the NEX Technology platform. We're kind of coining that like Intel inside, and really it's what the carbon nanotube technology enables. The CNT emitter is only one component in the NEX platform. That the emitter you can see there on the left-hand side of the screen. We have to then turn that into an X-ray tube, and it's very different to what conventional X-ray tubes look like and how they work. You'll get to see that as you walk around, but fundamentally we've had to invent how to do that, and it's very hard. Like all good new technology, it's not just the component that you're trying to introduce, you need to power it. So we have to develop our own generators. And then we have developed them into arrays and connect these arrays on and off and switch between sources so that we can actually replicate CT without having to rotate tubes around, and the right software to do it. So the NEX Technology platform really encompasses all of those elements. And as we grow as a business, I see the emitter as like the seed, and the tubes and the generators are like the trunk of the tree, and then the applications are the branches. As we grow and evolve, we'll be doing a lot more software than we will hardware, because that's really where we're going to go in the CT marketplace. So the CNT emitter itself is very, very unique. Research into CNT to generate basically electrons, that's all it does, has been going on probably since the 50s or the 60s. Back then everybody was using cathode ray technology. Nowadays, of course, people use silicon. And the idea was that we could basically miniaturize the cathode ray technology into tiny little source emitters and make miniature cathode rays. So back in the day, Samsung was thinking of making a pixelated TV, and each one having a miniature emitter, essentially, doing the same approach they do on a big wide projection screen. And the way they work is you have to concentrate high voltage fields onto the tip of something very, very small and conductive. Picture of it like a bed of nails of lightning rods. And in order to get enough current flow, you have to have enough of them in the right area, in the right distribution density over an area. And people have tried to do it. And the picture on the top left there shows all the other technology that we compete with. It's been around for a long time. Companies like NanoX, for example, they're using that old technology, silicon-based spin cone technology. It kind of works in the lab, but it's very, very difficult to scale. It's very difficult to get the density that you need of electrons, enough to generate enough X-rays out of an X-ray tube. And it's inherently unstable. So everyone else in the space is really struggling to get above 3 or 4 milliamps. Now, the milliamps are very important because to image a human, you need more than 100. You need 100 milliamps basically to do a chest X-ray. A CT probably around 300 or 400 milliamps. If your emitters are failing at 3 or 4 milliamps, you're nowhere near. And the unique part about micro-X technology and our NEX technology is we worked out how to do it using carbon nanotubes and create them in a very low-cost, easy manufacturing process that's very repeatable, that gives us a density and distribution in a chaotic fashion. And the core piece of patented IP that we own, it's a huge barrier to entry to everybody else, is shown on the bottom right-hand side there. It's essentially a glass matrix material, a special formulation that balances current and through a series of infinite resistance embedded in the material properties that stops the carbon nanotubes from ablating. When you grow nanotubes, they're essentially a graphene helix. They're all different lengths. It looks like the rough on my arm or something like that, or the rough grass on a golf course. By the time you want to use that tube, you have to trim that grass to look like a putting green. And inherently, that's how the other technology fails, because they're all different heights, it becomes unstable, and it just ablates. And it's that unique material, that glass material, that enables us to do that simply and effectively, and nobody else on the world can do it. The tubes themselves are complex. They're not really a tube. It's more like a Zener diode, if anyone knows what that is. That's how it actually works. We've developed 3 tubes now over the period of time. The first one on the left-hand side there is the tube that goes in our mobile X-ray. It has a range of performance characteristics. So it enables us to image something from a hand all the way up to a chest, or an abdomen, where you need higher power and lower power. You'll see when you hold one later, it's about the size of a can of beans. Weighs about 2 kilograms. The one in the center we developed for our security products. So initially for Argus, but now it's the same tube that's used in our security baggage scanning product. Slightly different, much lower current needed, but much higher voltage. 160,000 volts in something the size of half a tennis ball. It's quite remarkable. And the latest innovation, which we'll get to see today, is the mini tube, as we call it, or the cluster tube. This has a fixed performance characteristic, so we don't have to have the changing energy inside the tube, which is important because it means we can take that left-hand side mosaic tube and reduce it to about a quarter of the size. These are the tubes that we're connecting closely packed together to be able to make CT in a very compact fashion. The good news is, over the last 10 years or so, we know how to do it now. So to iterate tubes and make tubes is much faster. The discovery process has become a little less intensive. We still learn things as we miniaturize it. There are new physics we have to discover and work out, but we've built very sophisticated models that enable us to get there much more quickly. The generators themselves, they're not as cool looking as the tube, but very important because conventional generator technology is a limiting factor in most high voltage systems. We're delivering 120, 160,000 volts. We want it in something that's very small and very light. And a normal high voltage generator has a transformer which is full of oil. To get the same energy that our generators get would be 4 times the size, which is fine if you don't care, but it's really a problem if you want to move it around and make it portable. So we had to come up with a way of basically making new high voltage generators in a compact fashion. And we again used our knowledge in material formulation, and we come up with an epoxy, a special epoxy formulation which we call potting, where we're able to encapsulate the high voltage transformer boards inside this material and condense it all down. So whilst it's actually denser than oil, the overall impact because of the dielectric rating is significantly smaller, about 4 times smaller. We have the world's smallest constant source monoblock. What is that? That's essentially a tube and a generator connected together that you can turn it on and leave it on, and the X-rays just keep coming at low current. That's important because that's what you need for security imaging with a very high duty cycle versus imaging a part of your pathology, which is just essentially a flash. Now, this next slide, I think, is often underlooked. I'm just going to play a little video here. What we're developing is an array of tubes. That is what it's replacing. That is the inside of the CT without the cover. Stick yourself inside that. That is rotating around you at 300 revs a minute. Pretty scary. The ability to make potted arrays with small tubes and turn them on and off with fast pulsing very quickly means we can replicate that spinning thing with the thing on the left-hand side, a small array of tubes. And that's a significant game changer in terms of CT and being able to develop new products. We have the manufacturing facility, which you're going to tour around. Very important. Obviously, coming up with new technology in the lab is one thing. Being able to reproduce it consistently and reliably and for the right price is very important. We've had to develop all of this as well as part of our journey. These aren't things you can just buy off the shelf. No one was doing it before. So significant investment's been made. You'll see as you go around, some of it looks a little bit like a physics lab. Some of it looks more like a traditional production facility. Some of it looks like a wet chemistry lab. Put it all together, develop a process and automate it. We have a very scalable manufacturing process, and we're achieving extremely high yields and extremely high reliability and very favourable pricing. Every time we've looked to go and see whether we can explore working with another party to scale up the pricing, they can't even get close to our pricing. So it's very important for us as we look to the future that we have the right manufacturing process. And I'll just touch briefly on the imaging. We could stand here and talk for hours about imaging. What you can see there are the images that we presented to the Australian Stroke Alliance, captured using our CT test bench that you'll see later today. And that's showing pretty high resolution imaging. Little small white marks are actually small hemorrhages in the brain phantom that we have. You can see some of the structure of the sulci of the brain. You can see the intravascular system, and you can see a lot of the internal soft tissue structure. These are about 90% diagnostic at the moment. We're working on just tweaking them and getting them up to that next level. They are already better than the images they're getting in mobile stroke units, because those are very limited 8-slice or 16-slice CTs. We're probably closer to 120-slice CT in our image quality. This is where the company is going to really expand in the future with novel algorithms, improved algorithms. Yes, we'll start introducing more machine learning and neural network learning methods and things like that as we progress, but the medical industry is very sensitive around that kind of stuff. They want to see you actually give real data and turn it into a real image first, then apply all the fancy stuff later on. So that's the NEX technology. I'll briefly talk about the products that we make with it. You'll all be familiar with Rover. Obviously, we started the journey with the DRX Revolution Nano, the Carestream variant of essentially what Rover is now. That was kind of limited in power. It was designed as a workhorse unit that could go out and do everyday rounds, do lots of chest imaging, that kind of stuff. We've subsequently developed our own generator, and now we have what we call the Rover. It's all now certified. As I said earlier, over 400 systems sold. It is delivering extremely high image quality. It's very, very important. We talk a lot about our technology and our products, but what the end user cares about is the imaging. The X-ray imaging we're delivering is incredible. And not only that, we are dialing the technique settings back somewhere around 30 to 40% from existing equipment. It's a lower dose for better image quality. It's very important. It's less of an issue when you're talking about things like chest X-rays, because it's not actually a very high dose anyway, but it's very important when we move towards our CT. The next product, the miniature baggage scanner. Again, you get to see that today. We have shipped 2 of these now to the customer in the US, which is the TSA through the Department of Homeland Security. And the third system is here, almost fully built. We'll be shipping that very, very shortly. I think we probably delayed the shipment so it was available for today. And all intents and purposes, the scanning of the bags is going terrifically. The notion of this is basically you load as many bags in as you can, press the button, the door shuts, it spins around, 30 seconds later, it has done a complete CT of everything inside. If they can't quite see what they want to see, they want more resolution, they can do it again, they can spin it more times. The more times you rotate it, we keep flashing 6 tubes, the better the image quality. So lots of other applications for this as a technology. We'll focus on the baggage space first because that's who's funding the project. But you could use it for inspection systems. You could use it, we're talking to the meat processing industry, for example, about how they scan carcasses before they program robots to carve them up. Lots of different applications for the actual technology inside it. And further to the baggage scanner, of course, is our checkpoint. Now this is, you won't have seen these pictures. We haven't released these yet. This is our first fully built checkpoint screening portal. We have a mock-up of one here. This one's actually, it's just left Seattle and been installed in the TSL labs. And it's going terrifically well. Brian's actually there this week working with the customer there, going through experiments and using it. We have a sort of less pretty one over here in our facility that you can have a look at. It is blowing people's minds. Essentially, you can fit 3 people inside this. So it's designed to be like a passenger, maybe traveling with 2 children. Load all your bags in, press the button, and stand between those green panels. And just you moving around just like this is doing the millimeter wave. They do still make you do your arm like that because they want to see under your armpits. But essentially, it's fully self-contained, fully automated. And it's a really nice environment where you remain connected to your bag and you can do it in your own time. Because we can fit 8 of these in the same footprint as a conventional lane where you have to load and divest all your bags and go through the X-ray. So 8 times the throughput. There's probably, I think we've got contracted to deliver another, another 6, Kingsley, I think, of these. Another 3? Yeah, that's right. And essentially, if we get this right, it'll be demonstrated in a US airport probably in about 2 or 3 years' time. Now onto our head CT. This is where we think we're really going to be, it's a real game changer really for the whole industry, for patients and also for our business. You know, the cost in Australia alone of stroke is estimated about $9 billion per annum by the Stroke Foundation. It is the 2nd leading cause of death worldwide. 85% of strokes are ischemic, they are clots in the brain. And if treated with thrombolysis drugs, TPA, in the first hour, it dissolves the clot. I mean, essentially, there are stories where people are picked up on a mobile stroke unit in Melbourne within the hour, given the injection, and they walk off the ambulance before they even get to the hospital. It is that beneficial. The trouble is with that, because the clot grows over time, after the first hour, the benefits of the thrombolysis reduces. After about 2 or 3 hours, it's very ineffective, and they have to mechanically remove it out using a thrombectomy surgery. But 15% of bleeds. And the only way to diagnose whether it's a bleed or a clot after you've diagnosed it is a stroke is through an image. Yeah, you can use an MRI or you can use a CT. CT is a state of the art because it gives you the bone and the soft tissue structure, and pretty much anyone that presents with stroke gets a CT image to determine the stroke type. Mobile stroke units themselves are expensive, 1.5 million bucks or something to set one up, and about $1 million a year to run. Has a crew of about 5 people in. There's 2 in Melbourne now. There's none anywhere else in Australia. There's about 50 globally, and they are very successful in terms of their recovery rates and reduction of what they call disability-adjusted life years. We're talking about putting one in any ambulance because we can do it for a very low price and for under 70 kilograms. And what you can see here is the simple workflow from when the patient is retrieved to get in the actual exam. The CT exam is under 30 seconds. That vehicle you can see on the screen there is a standard Mercedes Sprinter ambulance, which is pretty much the stock standard ambulance across the planet. It's the smallest, there are bigger ones, and we've designed it in a way where it retrofits into the existing ambulance wall without really changing anything other than moving a few cabinets. So we're not talking about mobile stroke units anymore, we're talking about making any ambulance stroke capable, which is going to have terrific impact on patient outcomes. The test bench you'll get to see today, picture on the right-hand side there, we call it Leia. We have an affinity with Star Wars names in my engineering team for prototypes. We're almost finished building that unit. The picture on the right-hand side shows that the image, what it looked like when we were taking the phantom images of the heads. We're now putting some covers on, reducing all the wires, reducing all the circuit boards, doing the integration, turning it into the picture on the bottom left, which is a hospital integrated test bench. We're building 3 of those. The first one is Royal Melbourne Hospital, then the Royal Adelaide, then Box Hill. The plan is to install the first one by the end of June. It is subject to ethics approval. We've done all the pre-ethics work with the ASA and the Royal Melbourne Hospital. We just need to finish the build of this unit, do the final imaging measurements, radiation tests, and then off we go. The good news is the dose that we deliver is less than 1 millisievert. Now, 1 millisievert is the amount of radiation that you as a member of the general public are allowed to receive annually, just because from eating bananas or granite bench tops and things like that. I'm a radiation worker. I've got a license. I wear a badge. And the badge means I can have 19 millisieverts, so I don't know why. But we're delivering under 1 millisievert. A normal head CT was somewhere around 3 to 4 millisieverts, so 3 or 4 times your annual dose. Full body CT could be 10 times that. So again, dose efficiency, we're not wasting dose. We're not spinning things around at 300 revs per minute that weigh 150 kilograms. We have a 70 kilogram machine that fits neatly into the wall of an ambulance and takes a whole scan in under 8 seconds. And really the final product that we really are working on, and we announced recently, is related to full body CT. So it's taking that head CT technology, that novel array of sparse array of tubes, and turning them on and off, and turning it into a complete ring, which you can see embedded in the back of the vehicle. And this has been funded by ARPA-H. ARPA-H is the Advanced Research Programs Agency for Health. They were a spin-off of DARPA. DARPA is the Defence Advanced Research Programs Agency. They invented things like the internet and M16 rifles and the computer mouse. The US government decided that they really needed to try and invent things in health. It was on the back of the COVID pandemic. They did come out with their own COVID vaccine from their investment. They are addressing the need in the US in particular, which is the same here in Australia, of equity in healthcare across rural and regional parts of the country. And particularly in the US, where somewhere around, I think it's 30% of all rural hospitals are scheduled to close down because they simply don't have the funding to keep them open in the bricks and mortar. They want to move away from bricks and mortar, and they want to make essentially mini ICUs and screening centres and X-ray rooms on wheels that they can just move around to different areas so people can get their repetitive scans after they've had surgery, where they might be a couple of hundred k's away from where the hospital is. So that's a $25 million US project over 5 years. We've just started, and it takes us all the way through to FDA submission, because the final year of the program is in fact the Paradigm guys putting it into the vehicle and demonstrating it works, which is really happy for us, because it enables us to develop a full body CT for this, but also a full body CT that we could then look at deploying across any hospital environment. Very briefly, because we are short of time, I just thought I'd talk a little bit about the future. We're very focused, I want to iterate that, we are very focused on delivering the head CT and the baggage scanner. And of course, the ARPA-H project we see as an extension into the full body from the head CT technology. It is amazing the amount of awareness and contact we've had with the clinical fraternity globally in embarking on the head CT program. And our friends at the Stroke Alliance have been very helpful in propagating that information across the community. Lots of clinical people want to engage with us and do research. Now, because we have the NEX Technology platform, we can actually support that research with very limited effort. We can essentially provide equipment at cost, give it to them, they can conduct their research. When they prove it works, we can conceptualize new products in that CT space that they've already bought into and already done the clinical research. And we're partnering with people like Johns Hopkins and Mayo Clinic, people like that, University of Sydney ImageX, Monash Health Centre as well. All these guys, Flinders too actually, I should mention those as well, they're all involved in things like low dose lung screening, contrast enhanced breast CT. These are the latest steps in imaging, in diagnostic imaging, and our technology is really well suited to be able to basically provide products in that market space, which isn't that great big rotating CT that I showed you earlier. That's it, very brief, because we've got very short time. I'm happy to take any questions. No questions? No physics people in the room who want to ask me a difficult physics question? Yes. So in terms of our patent portfolio, I think I forget the number. We have a lot of patents around the emitter technology, particularly the material properties of that current sharing material. That's key, because that's a massive barrier to entry to anyone else who tries to replicate that. Other people can grow carbon nanotubes wherever they want. They'll suffer with the same problem of them ablating away. That current sharing material is a key patent. We have patents around certain design features of the rover. We have design registrations around rover. We have patents about how we control the switching electronics for the array as a barrier of entry to stop people from being able to try and replicate that with conventional technology, which they could do, but it would be much bigger. Yeah, I think all up, I think we've got about 17 different patents. Yeah, and most of them now, some are relatively new. Most of them have gone through what they call the PCT phase, which is this patent treaty, and they've gone into country filing. So we have registered patents now that will last probably another 18, 19 years in China, Brazil, Europe, Australia, US. Yeah. Right. Oh, here we go.
when are you going to test it in Adelaide Airport?
Yeah. We've talked to Adelaide Airport. They're quite interested in what we're doing. The airports themselves really rely on two things. They rely on the US government basically endorsing it and putting it into their system, or they rely on ECAC certification through the European agency. We're in the process of looking at pathways to accelerate through ECAC, in particularly with our partner Billion Prima, the Malaysian provider of security imaging. And also with Schiphol Airport, another group. The Schiphol Airport in Amsterdam is just seen around the world as one of the innovators in the airport space, so they're quite keen to help us get that ECAC certification. Once we have that, then we can look at putting it into airports and then actually running demonstrations.
With your plans to monetize your security side of this business,
Yep.
How do you anticipate something like self-spread and oil and the baggage things to actually evolve to that?
Yeah. Yeah, it's very well. I mean, Micro-X as a business, what we're really good at doing is we're really good at developing new technology, right? We want to maintain control of the manufacturing and of all our core technology, or our core IP, our tubes, our generators, our switching, our software. For Micro-X to suddenly become a company that's trying to install a massive infrastructure project into a single airport, let alone many airports, is a very, very far away from what we do. So we're trying to find the right partners in that space that can do that for us, and that's how we want to monetize the security CT. Ideally, we still maintain some form of supply arrangement, ongoing supply for the core technology, but in terms of the larger infrastructure rollout, that's how we're going to approach it.
So that'd be similar to Billion Prima?
Yeah, that's right. Yeah, Billion Prima is one example of that. Yeah, absolutely. Yes. Sorry? Yes, absolutely. You may have seen on the last slide there was a kind of defensive thing. So rover is already being used as part of the JP2060 procurement. I think we shipped 5 rovers to those guys, to Saab, basically as the prime contractor. That enables a deployed tented hospital, I think at Roll 2D. The CT product would upgrade that to a Roll 2E, so they're very, very interested. I was fortunate enough with the Stroke Alliance and the Stroke Foundation to go to Parliament House to try and secure some funding through the budget cycle, and the Stroke Foundation is actually chaired by Peter Cosgrove, and he took one look at the head CT and said, we need that in defence. So yes, again, defence, they're not really